back to linear maps. Just to get a sense of sort of how linear maps can generalize beyond what we're used to. All right, we got to get out of the habit of like y equals 2x, okay? So just to give a quick example, maybe like the linear map, let's call it D, all right? I'm gonna take D from polynomial to a polynomial, okay? How we write polynomial is usually this fancy looking P of a field, okay? We can say R, just for simplicity for now. So we're only dealing with an example. Okay, polynomial to other polynomial. This just means, this R here, it just means the coefficients of the polynomial are real, okay? And so that's like things like 1 plus 2x plus like 5x squared. We know what polynomials are, okay? And then you can take the derivative of a polynomial, right? I'm about to reveal the answer, what's going on here, while trying to take the derivative. But you notice, if you try to do this derivative in your head, you naturally take the derivative of this, then take the derivative of this, and take the derivative of this and add them together, okay? And how do you take the derivative of this? Well, usually take out that constant, you ignore it, and take the derivative of the thing involving x, okay? And then bring that constant back in, right? So what I'm trying to say is we're doing the derivative of 1 plus the derivative with respect to x, should have been saying, of 2x. Pull out that 2 plus, I'm just going to pull out the 5 directly, all right? The derivative with respect to x of x squared. And then you would just do that, all right? But you see how what we're doing, in a sense, if we call this derivative, I'm going to use the word operator. An operator is just a function from a set to itself, or going from polynomials to polynomials. We're writing this as d, okay? So this is just, we're doing d of 1 plus 2 times d of x plus 5 times d of x squared. So what we've just done is we've just demonstrated both of these properties, right? This property was that we can kind of distribute that function throughout each term. And this property was that we could pull out the constants. And so the derivative is an example of a linear map. It's interesting, okay? So again, just getting out of the habit of like the derivative or the linear map, y equals x. You know what I mean? Because y equals x, that's not our only linear function. We got interesting stuff like this. As a little exercise, do you guys want to try proving that the map T, also from polynomials on R, so polynomials on R, given by T of x equals, let's say, x squared times your polynomial. So I'm going to write it as, instead of x, since we're working with polynomials, I'm going to call polynomial p, going from one polynomial to another. T of your polynomial is just x squared times your polynomial, okay? Can I show that's linear? Be my guest. That's left as an exercise to the viewer. All right. Let's move on. I want to talk about some important sets involving maps. So we talk about domain and codomain, right? But we also talk about range, like what values, because you can have like a linear map and it sends values into like three-dimensional space, but it probably doesn't like reach all the values of that three-dimensional space, right? Like it misses out on some. Like in your domain, you can only reach so many values of R3 sometimes, right? And so we're interested in the range, the values that the function actually hits, right? Because if you're looking at like a line in 3D, okay, this is gonna be difficult to draw, I'm not gonna lie. I'm gonna draw this as like a dotted, let's say it's going like this, all right? Just try to use your creativity here to make up for my art non-skills. But you see how this line, okay, it's linear, it's going through the origin, but it's not like, for example, this point in three-dimensional space, it doesn't reach that. Okay, that's not in the range, but a point on the line is in the range. Okay, so get rid of this example. So what we mean by range, again, just to put it formally, so what is the range of some linear map T? Well, that's just going to be all values. Let's say T again is going from the domain X to Y codomain. Then the range is equal to, I'm going to say the range, so definition, the range of T is equal to the set of all Y in Y, so that we have that T of X equals Y for some X in the domain. Okay, so it's saying that all of the values in the range can be mapped to by some value in the domain, which makes sense, right? Okay, so that's our range. We've talked about subspaces on this channel. Subspaces are these nice forms of subsets of vector spaces, okay? And so you can show this as a subspace pretty easily. And I'll again leave that as an exercise. You know what, we can do it real quick though, because a subspace, remember, it preserves, it sort of facilitates linear maps in the sense, I never thought about it like that, but it facilitates linear maps in the sense that, like, if you add two things in a subspace and multiply a thing in a subspace by a constant, then it actually follows these properties, basically, almost. Because if you add two things in a subspace, it stays in the subspace. If you multiply it by a constant, it also stays in the subspace. So let's show that really quickly. So let's take any random y in our range. Okay, and let's take y1 and y2 in our range. If we add them together, does it stay? Like if it doesn't, then it's not a subspace and we have problems. Okay, so let's see. So let's do y1 plus y2. Well, what does this mean? This means that there exists an x1 in x, so that f of x1 is equal to y1. And same thing for here, but with the 1 replaced with the 2. So this is just f of, again, I can't be using f and t, we're sticking with t. So this is just t of x1 plus t of x2. All right, and we can actually use the linearity of t to pull out that t. This becomes t of x1 plus x2. Okay, now similarly, so we have this, okay? That means that y1 plus y2, we found something in the domain x1 plus x2. We know that if you add two things in a vector space, it stays in that vector space. So x1 plus x2 is in x, okay? That means that y1 and y2 is by definition in the range of t2 because we found some x, so that t of x equals y. Great. Equals, I should say, y1 plus y2, okay? Similarly, I'll actually leave this one as an exercise. Can you show this second property, all right? Or I should say, again, this property is similar to second property of a subspace, which is that t of, like, I should say, if you have y in the range, t, then is c times y also in the range of t. And for this, I'll give you a hint, you'll use that second property. Okay, so you should try that, I encourage you. Okay, so that's the range, it's a subspace. All right, we'll come back to it in a sec. Another thing I want to talk about is the null space. The null space, which is denoted null of a linear map T. By the way, one more comment on here. I missed one property. We're at, what, 9 minutes? Time flies, dog. An important property of a subspace is that it goes through 0. And you'll see that that just comes from this property. We know that t of 0 is equal to 0. So you'll know that 0 is definitely in the range of t, like, because you just plug in 0 to get 0. Okay, that's the last comment. Null space, okay, what is the null space? The null space It's in the name, it has to do with 0, right? Well, that also has something to do with the range, or with the function outputs of the linear map T. So this is actually pretty simple. This is the set of all, this thing lies in X, so the domain, not the codomain. So set of all X in X, again, T is from X to Y, so that T of X is equal to 0. Interesting, okay. So we're looking at the set of all function outputs that just get sent to 0. What the heck? Why do we care about that? That seems really lame. Well, I think this will become much more clear later on when we get into the fundamental theorem of linear maps. So that's a little bit of an ominous name. Don't get too excited, all right? All right, we're gonna get there. Hold your horses. But just to give you some idea of why we care about this right now, if you've ever taken like a pre-calculus class, maybe you've done systems of equations like 2x plus y plus z equals 0, like x minus y minus z equals 0. So again, like for example, system of 3 equations with 3 variables, maybe like y plus z equals 0. I don't even know if this has a solution. Something like this, right? And you want to solve for x, y, z, okay? Well, maybe what you did, right, is you turn it into a matrix, 3 by 3 matrix. You did x, y, z. You set that equal to 0, okay? Well, what you've just done is, we'll see that matrices are actually just linear functions, okay? What you've done is you're looking for all things in the null space of that matrix, of that linear function, okay, in that linear map. And these are interchangeable, because you're looking for all outputs that get sent to 0. And this is useful, okay? That's why we care about the null space. Null space, again, it's a subspace. This is a very similar proof to this, so I'll leave that as an exercise. But the null space, okay? The null space is cool. It's also useful because it tells us if a linear map is injective, okay? This thing also kind of tells us if a linear map is surjective, okay? I'll remind you what these mean. So surjective means, I mentioned earlier that sometimes linear maps don't take up the full space that they get sent to. They leave out some stuff, but sometimes they do, and those are called surjective functions. And that's really clear because a function is surjective if it hits everything in y in its codomain. And if range of t is equal to y, that means it's surjective. And that makes really intuitive sense just by the definition. However, null space tells us about injectivity. So what is injectivity, you might ask? Well, sometimes you've heard the term one-to-one, okay? If you look at a parabola, for example, just y equals like x squared. That's not a linear function, but I'm just trying to make a point here. So if you look at, like, for example, here, let's say this is -1, this is 1. -1 squared is equal to 1, but 1 squared is also equal to 1. That's not injective because 2 points get mapped to the same function. And the point of an injective function is that it maps every point to a different value. So something like y equals x cubed, that is injective because if you notice, everything gets mapped to a new thing. Okay. So how do we tell if a function's injective using linear maps and not having to worry about, a specific type of set that we're working with? Okay, so this is a theorem. This is a result. So a linear map T is injective, again, 1-to-1, if and only if T, I should say the null space, null of T is just equal to the set 0. What does that mean? That means that the only thing that gets sent to 0 in the codomain, y, is just 0, okay? So we know T of 0 is 0. So this always holds. So there's no other value that does that. And that makes sense because if there was another value, like if T of x was equal to 0 and x wasn't 0, that means we're sending 2 points to the same point, and that's not injective. That makes sense. That makes intuitive sense, but one has to prove things like this. And prove it in the next video. I'll be back.